In episode 2, we seek to answer the question, why do we need quantum computing? Topics covered include examples of the limitations of classical computing, the different types of quantum computing that have emerged, the problems that can be solved with quantum computing, and how quantum computing is likely to change our lives in the future. Welcome to Entangled Things, your quantum computing podcast, hosted by Patrick and Ciprian.
So Ciprian, what are we talking about today?
Well, today we're going to talk about why do we need quantum computing. We're going to try to get into more details around the reasons why classical computing is not enough and why is quantum computing so important when it comes to promises to solve problems that classical computing simply cannot.
So we're going to answer the question, if it's not broke, don't fix it. And, what's going on and what can quantum add to what seems to be the biggest revolution in human history anyways.
Yeah.
So what do you think is the biggest limitation of classical silicon-based computing?
Well, I would say the biggest limitation of classical computing is complexity. If you remember on our last discussion, we provided that example with simulating the behavior of systems of various sizes, and even for
I remember that
for systems that behave in a statistical way, right? Which are basically any kind of natural systems, and even for a small number of components, the complexity of the problem that is measured in the amount of memory locations that are needed, the amount of computation that is needed, goes far beyond the capabilities of classical computers. And those problems happen to be very, very important problems for the human race. Remember, we mentioned about agriculture and fertilizers. We talked a little bit about material science. We talked a little bit about other types of simulations of chemical and physical phenomena. So those are all very, very important for the future of mankind. And we still cannot, we don't even get close to solving those using classical computing.
I agree with that. I think that if you wanted to summarize it a little bit, you might look at it from the hard sciences. So if you add computing, regular silicon computing, to any field of knowledge, we've seen exponential growth in its ability to progress. When you add Moore's law to medicine, when you add Moore's law to physics, when you add it to almost anything, you get an exponential increase. And that's why we're curing cancers at record rates, et cetera. But one of the areas that hasn't really jumped forward as much, it's progressed and it's definitely benefited, is chemistry. Because of what you're talking about, because of the modeling problem, because of the discovery problem, and maybe physics as well, though I think probably not as much as chemistry. So material science, chemistry, is going to be the big beneficiary. And then security, my area, because it's a lot of people think that quantum is bad for security, but ultimately it's probably going to be a lot better. But yeah, by hurting shared key encryption, we're opening up a whole new world of different encryption. And so anytime someone says, well, you can't do that, it's not, we won't be able to do that in the near future, it's probably a place where quantum can do a better job.
Yeah. And then if you think from a more, let's say, formalized perspective, we all know that when it comes to classical computing, we have two major classes of problems, the so-called P and NP. P standing for polynomial time problems, NP for non-polynomial time problems. And that simply means that the polynomial problems, the P class, can be efficiently solved by a classical computer, while the NP, or the non-polynomial class of problems, cannot be solved in polynomial time, which means that for those problems, you get to the point where getting a solution can take hundreds of years, thousands of years, 10,000s of years, with no matter how much classical computing capacity. And that's where quantum computing comes in. And actually, in terms of the formalism around the complexity of problems, now we start seeing a brand new class of problems, which is called BQP, which stands for Bounded Error Quantum Polynomial Time. It simply defines problems that quantum computers can solve in polynomial times, and where a quantum computer can solve a problem in polynomial time that a classical computer cannot, that is where you see the huge value and the huge potential of quantum computing.
So, how many credits of math can our listeners get from this? There's a lot of math going on that you're talking about some concepts that are hard for a lot of people to understand. I guess the thing that I take from it is quantum computing is not going to supplant classical computing. It's not like you're going to have a quantum computer at 3 millikelvin or 30 millikelvin on your wrist or in your pocket, but it's going to supplement and solve the problems that can't be done, can't be solved. And so they'll work together. It's kind of like the graphics card is a specialized calculating system for your computer, but it doesn't replace the GPU or the CPU. Sorry, CPU.
Oh yeah, yeah. You're absolutely right, Patrick. Unfortunately I've heard many times this theory that when quantum computing becomes a thing, everything will be replaced. We need to forget everything that we know about classical computing. We need to forget everything we've done with classical computing, and that is as far from the truth as possible. Quantum computing has the promise of bringing solutions to some of the difficult problems that we have today. But for example, when it comes to working with classical data, to give you just a simple example, a quantum computer is absolutely helpless. So I don't foresee, for example, a quantum computer replacing a classical computer that runs a modern data warehouse, just to give one example here.
Yeah, you've mentioned in the past that one of the big limitations, and we don't talk about limitations of quantum too often because we're too busy thinking of its possibilities, is it doesn't really read data and process data. You have to tell it, you have to set it up like, it almost feels like you have to set it up like a domino system where it has no memory, it has no ability to read from disk, it can't process a file. You basically do set piece calculations, and then you have to take the results from that and add it to something else, typically a classical computing program. If you take Shor's algorithm, the one that does the factoring of large primes, it isn't going to crack communications. It's going to allow you to quickly take the step that is part of cracking those communications, do that on the quantum computing, feed it back into the regular silicon-based computer, and then crack the code quickly and easily. But it's not end to end. Neither of them. They're kind of they're codependent, is what I might say.
Yeah, and that's so true that quantum computers have no ability to work on data as we know it. And when we refer to data as we know it, we refer to data that is represented using bits. And that's because of that fabulous property of any kind of quantum system. We're talking here about the fact that when you try to measure the state of the quantum system, you will actually end up with the system collapsing, and you will get a combination of the fundamental of the basic states. Now, it's also true that quantum computers will be able to work on quantum data, that is data that is generated from quantum systems. And that, again, is another argument why we say the two of them will live together, because virtually all data that we have now in the world is data that is based on a classical computing representation, which is using bits, zeros and ones.
It's funny because it's almost like Newtonian physics versus quantum, in that most of our lives are dictated by Newtonian, and we didn't throw it away once we discovered the quantum effects at the microscopic level. But when we have them both, we get amazing things like MRIs and all sorts of technologies. One of the things that I fear, especially when listening, even when listening to our podcast, which is meant to bring this down to the level where people can understand it and get on board, is the fact that somebody might listen to these podcasts and say, well, I'm not going to be a physicist that's understanding this kind of stuff. So I'm just going to stick to my corner. And I would say that that's a bad takeaway. I think the right takeaway is right now, this stuff is cutting edge. It's bleeding edge. It's hard to understand. It's hard to wrap your head around. But we're going to need more people who understand this, even at an elementary level, than we're probably going to be able to train for the rest of my life. Once this tipping point happens, once this becomes an actual technology that lends solutions to life, the scramble is going to be on to get people, and they don't all have to have MIT degrees.
No.
And so one of the things that we're going to have to do is make sure we leave some room here for people to understand the practical side. And I know you're good at that, but sometimes we're gonna tip our toes in the math side, but we'll try not to live there.
Yeah, and the other thing that I would like to add here, Patrick, is the evolution will be very, very similar, I believe, with the evolution of classical computing. If you're, let me show you an example from my field of expertise, from machine learning. Today,
Before you do, I'm sorry. What you just said is very important, because if I talk to some of the old timers, they talk about programming in binary, which I'm not really interested in doing myself. But you're basically saying that what's going to happen in the future with quantum is it's going to come down to earth, and there are going to be interfaces that make it easier to deal with.
exactly. And I have
I'm sorry. Go.
Yeah, I have a great example from classical computing, actually from machine learning. One of the most complex areas of machine learning today is deep learning. The math behind training a deep learning neural network is really, really complex. It comes down to calculus, to derivatives, to very complex algebra. But as of today, an average developer can take a library like, for example, Keras, and use 5 or 6 lines of code that will literally build and train that deep neural network, that machine learning model, without actually knowing anything about the complexity of the underlying math. And that's a great example. And I believe that quantum computing will evolve along the same lines. Today, yeah, we're talking about the weird properties of matter and the weird quantum phenomena and about quantum gates and things like that. At some point, we will have levels of abstraction that will hide all this. And programming using the power of quantum computing will be basically available for everybody. Because if it's not, then quantum computing will prove to be a failure.
Yes. But that doesn't mean that you shouldn't start paying attention to it now. Because the more of this down and dirty stuff you can understand, the more common sense the abstractions will be. The more they'll make sense.
Yeah, and let's just quickly enumerate some of the fields where you can have solutions based on quantum computing. The most important one, I believe, is the one that you mentioned tied to chemistry, which is quantum simulation, right? Quantum computers, they use quantum phenomena in their inner working. So it's almost natural to think about them being used for simulating the behavior of molecular formations or of superconductors or things like that. And then cryptography, which we'll probably cover a little bit later in this episode. And then there is search. the simple problem of search can be significantly optimized with quantum computing. And then there is quantum machine learning. We already have some interesting results over there. And last but not least is a field that is called today quantum-inspired computing and optimizations, which basically is about designing and implementing new approaches in classical computing that are based or inspired from quantum computing. So looking at these fields, we can see that it's a very, very, very important quest that we're going through in this period of time. And hopefully quantum computing will help us address these very important problems.
So it's interesting, that last point. You and I, the last time we were at a conference together, I think it was a build, Microsoft Build up in Seattle. And there was an organization named One Qubit out of Vancouver that spoke. And they're doing exactly what you're talking about. They're taking silicon simulations, basically a computer that simulates a quantum computer, and they're programming algorithms against that quantum model. And they're claiming that they see an 8% increase in performance, even without the quantum effects. And so there's a lot of things that I never would have guessed. I never would have imagined that. But those are advantages that we can realize even before we get to the general quantum computing. So let's talk about the difference here between two of the big buzzwords. So there's general quantum or quantum computing, universal quantum computing, and then there's quantum annealing. So how would you explain that to someone who is just getting their feet wet?
Well, when you talk about a universal computing paradigm, it's basically a computing paradigm that is capable of writing or developing any kind of algorithm based on some fundamental building blocks. And that's how we got to universal classical computing, because it is provable that using a combination of the fundamental gates that operate on bits, you can actually implement any algorithm. And fortunately, this theoretical result is also available for quantum computing. So this is already accepted that there are combinations, there's a set of fundamental quantum gates that operate on quantum qubits, which you could use to approximate any algorithm to a very, very, very small amount of difference. And that's basically universal quantum computing. The other approach that you mentioned, which is called quantum annealing, is basically a process where a very specific problem is solved. To be more accurate, an optimization problem is being solved. So a quantum annealer or a quantum annealing computer will not be able to solve any kind of quantum problem. It is only able to solve a very specific subset of all the problems, which is the problem of optimization.
And so when we get, this helps make sense of a lot of the headlines. We have organizations like IBM that we mentioned in the last show, and we'll probably mention quite a lot, who are working on an actual universal quantum computer. And they're talking about having, 50, less than 100 qubits operational. But then there's other organizations that are doing quantum annealing that will, without really differentiating in the headline, they'll talk about having thousands of qubits operational already. And it isn't to say that IBM is behind, it's that they're doing the harder work that's going to take more time. And so, if I understand correctly, is it DWave that is the lead in quantum annealing right now, and they're backed by Google?
Yeah. DWave is the one that builds to date the most advanced quantum annealing processors, and have probably the most important results in this particular field, which again, without obviously taking out any of the credits for this work, is a quantum computing approach that is capable of just solving that particular problem. Now, having said that, that particular problem of optimization in itself has a tremendous number of applications in real life, right? So even with quantum annealing, we're already capable of using the power of quantum phenomena to solve real world problems.
So just to give an example, the quantum annealing is about finding local minimum. So if you make an example of that, it would be like, I want to find the best route for a delivery from one side of Chicago to the other side of Chicago, taking into consideration, streets and average times and things like that. It gets you a better path, the most efficient path. Whereas you can do that with silicon as well, but it's faster with quantum. It's a quantum speed up is what you could get there. And so it can't do general computing, but it can do those kinds of local minimum calculations for efficiency.
Exactly.
And that's used everywhere. That's used all over the place. We don't notice it. It's not sexy probably, but it's used all over the place for optimization and search and things like that.
Exactly. And the way that the quantum annealing process works is, think about having a system of multiple quantum annealing style qubits, and then it evolves them in a certain way. So that system evolves through time, and at some point it reaches a state that can describe the solution. That's the fundamental way that this system is working. And that's why you have those larger number of qubits in quantum annealing systems, because the limitations, the requirements regarding, for instance, the stability, regarding the isolation to external phenomena and so forth, are more relaxed than the requirements for universal quantum computings.
Yeah, my understanding is it's more, they lay them out as a matrix or a lattice. And so I'm not going to pretend I can explain it in a few words, but it's definitely a different design. It's a different tolerance, I guess is a good word.
Exactly.
It can allow a lot more noise.
Think about it as a more relaxed set of constraints that are put on the physical system, which is the quantum annealing computer, as compared to a universal quantum computer. And that's why they are relatively easier to build, and also they can have a significantly larger number of quantum annealing qubits. Cool.
So let's shift gears to.
By the way,
oh, go ahead,
Patrick. You mentioned Shor's algorithm, right? Which in fact in quantum computing, Peter Shor's algorithm is an algorithm that is used for solving the factorization problem, right? Now, yes. A quantum annealing computer, for example, cannot implement Shor's algorithm. And
good example.
Yeah. And the main reason why a quantum annealing processor would not be able to do that is because Shor's algorithm is not what we call a hill climbing process, is not essentially a pure optimization process. Because it is not an optimization process, it cannot be implemented with a quantum annealing computer.
Right. So it's like you can't run Halo on a graphing calculator.
Exactly. Yeah, that's a great analogy.
So let's shift gears and talk about, because you kind of broached the subject, the problem solved in quantum. So we just talked about let's talk about factoring. So security, encryption is all about factoring. Big, large factors, and public key encryption, public-private key encryption. Um, Not to get too deep into it, but and we'll probably dive very deep into it in a future show. Um, Basically, I take a enormous prime number and have two factors for it that are also enormously large numbers. And a gross simplification is that one of those is the public key and one is the private key. Um, and the fact that they're so big and there's so many prime numbers means that a regular computer would take 10,000 years to calculate the primes that would make it up to, so that given the public key, you could calculate the private key. And quantum cuts through that through Shor's algorithm because it would allow a qubit system, a system defined by a few hundred qubits. And I think the last time you and I discussed this, I think we were talking about 500 qubits probably would be enough of a stable universal quantum computing to eviscerate a public-private key. And if that were the case, then that nobody's secrets would be safe if they're using public-private key. Well, that means SSL doesn't work to protect you. It means that signing of documents and those kinds of encryptions don't work. Some encryptions still work. That's an example that a lot of people know about. It's actually an example that's driving most of the people I know in the military space and the security space to pay attention to this. Because without Shor's algorithm, I don't think a lot of the security people would even pay any heed to this. But it actually is going to be a big deal in the security space. But what about search? You mentioned search, and I'll admit that I know much less about the search aspects than the secure aspects.
Yeah, so at the heart of the search approach in quantum computing is what is now known as Grover's search algorithm. And basically what this does is it allows you to solve the problem of search, finding an item that obeys a certain condition from a certain list in fewer steps than are required by even the best known approach in classical computing. Now, what's important to understand with search is that, at least based on what we know right now, the improvement is not that spectacular. So Grover's search algorithm will not, let's say, improve the speed in a spectacular way, but it does improve in a significant way. So, and the whole idea behind the approach of the search algorithm is to initialize the state of the quantum computer in a way that, after performing a number of iterations, which are called Grover iterations, the state of the quantum computer will be set in such a way that through a measurement, you can identify the solution for the problem. And this is a more moderate example, which I particularly like a lot, because it's an example of how quantum computer can significantly improve, but it also kind of keeps us with our feet on the ground. That's why I think the search algorithm is a very, very important one.
So this begs the question of, how can you make good use of search if we can't read data?
Yeah, so with the search algorithm in quantum computing, it is very, very important to make a distinction between finding a solution and recognizing a solution. And that's one of the subtleties of the search problem. Think about a simple example, right? I have like 10 apples that I put in front of you, and let's say one of those apples has a different color than the others, right? Recognizing a solution means that if I take an apple and show it to you and ask you, hey, Patrick, is this the apple that has a different color than the others, you will be able to say yes or no, right? That's recognizing the solution. Now, finding the solution obviously is a more difficult process. Think about now about a situation that I cannot see those apples, but I can take them and show them to you, right? So then the way you could approach the problem is I could try every single apple, take it in my hand, show it to you. Remember, I don't see the color, and ask you, hey, Patrick, is this the solution? You would say yes or no. And then we know that on average, after a certain number of tries, we will find the solution. And that's the important thing that the search algorithm plays on. And the recognizer, so to speak, of the solution in quantum computing is called an oracle. It is a piece of a quantum code that is capable of recognizing the solution.
Right. I find it still happens in the journey of learning and understanding quantum that your mind takes off into these things of, well, I don't understand this whole area, and it gets hand wavy, and you have to bring yourself back down. Now, you had an excellent anecdote of your math professor, or was it an AI professor, who helped you understand that you can't understand it the way you understand other things. Do you remember that anecdote?
Oh, sure. And the story is like this. I was in my early years. I was studying a lot of quantum physics, and I was obviously starting with the mathematical fundamentals and everything. And there is a book about quantum computing. It's called Quantum Computation and Quantum Information. It's written by Michael Nielsen and Isaac Chung. It's considered to be the textbook for quantum computing. And I was trying to go through the book, and after the first 100 pages or so, every time I stalled, and then I let it go for a couple of months or even a half a year, try it again. And at some point, I had this discussion with a professor of quantum physics from the local university of my town, and I was like, I am not able to grasp this. I think I'm smart enough. I think my level of logical and mathematical intelligence is good enough for me to go through this, yet I cannot understand. And he smiled to me and he said, I bet most of the time, or the question that you ask yourself most of the time is why. And I was like, yeah. Well, forget about the why, and you will be able to progress. And the reality is that some of the things, even in theory, in practice, in experiments with quantum physics in general, and also with quantum computing, are the only answer to the why is because that's how nature works. The moment I was able to kind of leave aside the why and concentrate on the actual theory, I was able to progress.
Einstein had many of the same problems. He didn't accept his own discovery because it didn't make sense in the universe that he grew up in.
It's a fabulous example, Patrick. The math was in front of him. The math was correct, right? And simply because he was
track his observations,
he was not able to grasp with the why. Why does nature work in an undeterministic way, right? That led to the famous God does not play dice.
And yet he does.
Apparently so. Yeah.
So we've talked about theoretical, and that's what we're coming from. What about practical? We've touched on this a little bit. How is it going to affect global warming? How are we going to be Telecommunications, we talked about secure communications. There's a whole bunch about entanglement that we're going to have to talk about, and things that people think from popular sci-fi would work, but that the theories tell us won't work. Um, is and we don't want to spend too much time on this, but is there anything that stands out that we haven't mentioned that you'd like to bring up about the practical fields? I'd like to start by saying I think the space elevator is going to come to fruition through the material science advancements that we'll get from quantum computing. And I think Kevlar and rayon and nylon and all those we're gonna have new materials like that times per day instead of times per decade.
I fully agree, Patrick. I'm a firm believer in the fact that the solutions to the big problems of humanity will not be discovered. They will be computed. And I think we've already talked in our first episode of Entangled Things about fertilizers and about how kind of limited we are today in terms of the chemical formulas that we are using for fertilizers, and how efficient is nature's fertilizer, the FEMOCO molecule. And the main reason why we cannot yet create something that behaves in a way that nature's fertilizer is because we simply cannot simulate the behavior of that molecule. And because we cannot simulate it, we cannot create something that works in a similar way. And when you think about new materials, whether they are for agriculture, for space elevator, or for medicine, right? This is one of the huge promises of quantum computing. And this is why I believe humanity, like as the human race, should kind of rally behind the concept and the idea of we need to make quantum computing, universal quantum computing, a thing, a real thing. And without using big words, I think our long-term future depends on this.
Okay, so let's back it up, and because we're going to wrap up with how will it change our lives, but I want to change that a little bit to when will it change our lives, and I know you and I can't perfectly predict, but um, if quantum computing became a normative thing, something that was a tool that was available tomorrow, if the quantum computing that IBM and Microsoft were doing, if they had 3,000, 5,000, 10,000 qubits stable, available, error corrected. I think that the lag time, the problem with getting it to really change our lives is the community of people necessary to operate it, the programmers, the quantum computing experts who hopefully are listening to this podcast, and the budding aspirational experts who may eventually evolve. That's the problem. I think the technology is gonna evolve much faster and much more surprisingly than the people who can actually wield it. Do you see that as the limitation, or do you think it's the technical limitation is gonna be what constrains us?
I can certainly agree with you in that our capability of keeping the pace with the actual technology, that the technology to build quantum computers is one of the big risks.
It's a variable.
Yeah. And it's not entirely, although we have very encouraging results, right? We're not yet 100% sure that we can build universal quantum computers with large number of stable qubits. That's yet to be proven, right? Theoretically, we believe we can. Practically, we're not there yet. But coming back to this risk, this is why I believe that initiatives like Microsoft's quantum initiative are so important. Think about it. Microsoft has already built a quantum SDK. Microsoft has already built a quantum programming language, the Q#.
Right.
And you can already, using your popular tools like Visual Studio, for example, you can already write and design and think about quantum programs and quantum algorithms. The only limitation that you have is the last stage, which at some point will need to be an actual quantum computer, is now a simulator that uses classical computing to simulate probabilistic behavior. And that's why you are limited to a very small number of logical qubits. But having said that, steps are already done towards starting to build the infrastructure in terms of software, tooling, languages, and ultimately communities that will be able to leverage all this. And one huge signal is that, Microsoft's most valuable professional program, for the first time, included since last year contributions in the area of quantum computing. And it's not only Microsoft that does this. You see initiatives from IBM, you see initiatives from Google and the other players, and they are very important.
So maybe that's the thing. If we get the big breakthrough that enables larger universal quantum computing, maybe we're still playing catch up. But if people avail themselves of these tools, and you and I avoid scaring too many people away with our deep subjects sometimes, we might be able to have the manpower to do this once the hardware arrives. I think we're about out of time now. Is there anything else you want to add before we sign off till next time?
No, I think we covered a lot in this episode, and I really hope that our listeners have now a tiny little more of an understanding of why is it important to have quantum computing as a real thing.
I think we're working towards that.
Absolutely.
We'll talk to you next time. Thanks a lot, Ciprian.
Thank you, Patrick.